Look at this array of cables. In the early days of computing, processing information meant physically rewiring massive mainframes by hand. While mechanical bottlenecks are gone, we now face a conceptual one: the challenge of processing massive, chaotic streams of unstructured data. For decades, classical statistics excelled with small, structured datasets, clean rows of numbers mapping to linear regressions. But modern data doesn't live in spreadsheets. We have to bring our models directly to this unrefined data. When you force high-dimensional pixel arrays into linear equations, traditional models break. They lack the dimensional capacity to process that complexity. Deep learning represents the architectural expansion of those classical principles, re-engineered specifically to process the immense scale of modern information. Understanding how these models actually function requires dismantling the network back to its 1940s foundations to see the engineering bottlenecks it broke through. We start at the foundation, the perceptron. Developed in the 1940s, it functions as a basic linear classifier. It takes input features and tries to draw a straight line to separate different categories of data. This chart shows a scatter plot of a simple two-class dataset, plotted on a coordinate plane with purple and yellow dots. The perceptron learns to separate these classes iteratively. It makes a prediction, calculates the error, and updates its internal weights based on that specific mistake. This process is the direct ancestor of stochastic gradient descent. If the perceptron misclassifies an observation, say placing a purple dot on the yellow side of the line, it applies a mathematical penalty. It then literally tilts the classification boundary to correct that specific error for the next pass. The system works flawlessly until the underlying data becomes slightly more complex. If the categories cannot be separated by a perfectly straight line, like a bullseye pattern, the perceptron fails completely. The algorithm gets stuck in an infinite loop of overcorrections. Because true mathematical convergence is impossible here, engineers had to program hard stop criteria, like a maximum number of epochs, just to force the system to halt. This strict reliance on linear separation stalled progress in neural networks for decades. To process truly complex, nonlinear data, researchers realized they could no longer rely on a single classifier. They needed to stack them. By chaining multiple perceptrons together, the outputs of one layer become the inputs for the next. These intermediate stages are what we call hidden layers, and they grant the model the geometric flexibility to wrap around highly irregular data patterns. We measure the scale of these networks through two dimensions. Width is the number of nodes in a single layer. Depth is the total number of sequential layers. This stacked architecture is exactly where the term deep learning originates. But stacking layers introduces a massive optimization problem. When you expand from 2 or 3 weights to a dense web of millions of interconnected parameters, figuring out exactly which node caused a bad prediction becomes a logistical nightmare. We solve this using a loss function, like categorical cross-entropy, which calculates the total error of the network's final output. Through a process called backpropagation, that error signal travels in reverse through the network, updating the specific weight of every single connection based on how much it contributed to the mistake. Computing this for an entire modern dataset at once would overwhelm a standard processor. Instead, the data is chopped into small mini-batches of perhaps 128 or 256 images. The network updates its weights after each batch, cycling through the complete dataset over multiple passes, known as epochs. The depth of the network provides the mathematical capacity to learn complex data. But it is these iterative optimizers, methods like stochastic gradient descent in ADAM, that allow us to actually navigate a landscape of millions of variables and find the correct answers. Even with backpropagation, deep networks hit another wall. Adding hundreds of layers is useless if the error signal decays before it can reach the front of the network. Historically, developers used activation functions like the sigmoid curve to process signals between nodes. Because sigmoid squashes output values into a very tight, smooth range, the error signal is repeatedly dampened as it travels backward until it disappears. This creates the vanishing gradient problem. The layers closest to the data input receive no mathematical updates. They freeze, stalling the learning process from the start. The engineering fix was to swap the complex curve for the rectified linear unit, or ReLU. It operates on a simple rule. If a number is negative, make it 0. If it's positive, leave it alone. This unconstrained, linear response prevents the gradient from shrinking as it multiplies backward. Replacing a complex curve with a computationally cheap threshold preserved the error signal and finally made training massive, multi-layered networks viable. Once the signal flows perfectly, we run into the opposite problem. A deep network equipped with millions of parameters has an astonishing capacity to learn, so much so that it will often bypass actual logic and simply memorize the training data line by line. We call this extreme overfitting. The network conforms so tightly to the specific dataset it was trained on that it begins mapping the random statistical noise and unique quirks of the samples, rather than identifying the underlying patterns. To force the model to generalize, architects introduced a technique called dropout. During training, a preset proportion of the active nodes, say 30 or 40%, are randomly deactivated at each layer. The network can no longer rely on a specific pathway to make a prediction, because that pathway might randomly disappear. It forces the remaining nodes to learn broader features. For statisticians, it is the neural equivalent of random forest feature bagging. Engineers also employ temporal safeguards, like early stopping. We monitor the model's accuracy on a separate validation dataset, and the moment that validation error begins to rise, while training error continues dropping, we halt the training epochs immediately. Without these constraints, deep networks would be mathematically overpowered to the point of uselessness. Dropout and regularization are the vital engineering brakes that tether these massive computational models to statistical reality. When you assemble all these pieces, the architecture of modern deep learning is remarkably straightforward. It is a stack of linear models activated by sharp ReLU thresholds, optimized iteratively by many-batch gradient descent, and strictly constrained by dropout. This brings up a question of timing. If the foundational math for this pipeline has existed since the mid-20th century, why did it only begin producing near human-level results after 2010? The millions of parameters in a deep network require incredibly intensive continuous matrix multiplication. It took decades for the parallel processing capabilities of modern GPUs to reach the threshold required to calculate these equations at scale. The internet age then provided the last required ingredient. These architectures are data-hungry, and the web finally supplied the millions of accurately labeled images and text files needed to actually train them without stalling. Deep learning is the result of taking foundational statistical theories, identifying their mechanical bottlenecks, and resolving them with an overwhelming application of modern computational engineering.